Okay, welcome everybody. Is it on yet? It looks like it is. But can you puedes ayudarme con las luces, por favor? No sé cuál es. Ah, esto. Sí. Yep, gracias. Anti-doping? Anti-doping? Is that what you said?
No. It is talking about falta a la integridad. What does that mean?
Yeah, you're talking about that. It sounded like you said anti-doping.
I said it.
Okay. I was going to say, what Spanish phrase rhymes with anti-doping? Nothing. Okay, in the homework, you're going to have a, wow. You're going to have, there we go. In the homework, you're going to have a problem. This is like almost too small to see, and none of the colors showed up. That's really strange. Let me get out of this and see if we can just do it the old-fashioned way. Okay. Yet the colors show up here, so go figure. I don't know why. I need to show you what's going on in this diagram so you can do the homework problem. Otherwise, it's not going to make any sense. And if I can't explain this to you well enough, then I'm going to eliminate it from the homework. So if I can't explain it, then how in the world are you supposed to do it? It's like the way I think.
Oh, Dad, I see that.
So this is a buffer chart for a receiver on a streaming application. And it shows time going across the bottom and the size of the buffer, how full the buffer is. So we don't really know how big the buffer is, but what we know is that at time 1, nothing happens, but during the second, we receive a packet number 1. And I color it green so you know it's new. Packet 1 is going to stay there in the buffer until someone pulls it out. And they're not going to pull it out of the buffer until time 19. And I'll explain why that time. In time number 3, packet 2 shows up, and then more and more packets show up. So you build up a bigger and bigger buffer. The packets are sent 10 at a time in a window, and at the sender, they're sent back to back. You know, back to back? Like right after each other with no delay. But we can see at the receiver, there was a delay. There was a delay of 1, 2, 3, 4 seconds where nothing new arrived. And then after those 4 seconds, on the 5th second, another packet 1 showed up. So this is the second set of 10 packets. And they show up until number 10, and then there's a 1 second delay, and then the third round of 10 packets show up. So 30 packets in total, 10, 10, and 10, with some delay in between.
Why does like a there and the other one work?
So we'll talk exactly about that. So let me take a screen snapshot of this so I can draw on it a little more easily. And I need you to be able to understand exactly what's happening here. Sorry, I've got a computer architecture class that's I'm also showing here. So yeah, I teach doctoral students even, if you can believe that. They let me near people, real adults, like actual grown-ups. I can talk to them and everything, and that's pretty fun. Okay, so why am I having a hard time moving this over? There we go. All right. So I'm going to paste this in, and we're going to answer his very good question, which is why does it go up like a staircase and then start flattening off? Tell me. I was going to ask if anybody knew.
It's like getting the instructions, and once you pass another one, stops operating the one.
Very close, right? So that's a decent answer. So what's happening here is I'm just building up, I'm accumulating packets. With streaming, you don't start sending it to the television screen as soon as it shows up. You need to maintain a buffer because things don't always come in at an even rate. Sometimes there's moments when nothing shows up and you need what's in the buffer to keep from stopping in the middle of the movie. So the trick is to figure out how much buffer do you need to build before the user becomes impatient, and yet have enough in the buffer so that you never run out during the movie. And the network is changing the whole time. So this is a hard problem. It's what we talked about last time. So what this system decided to do was to wait for one entire set of 10 packets to arrive and then wait 8 seconds more. That's their rule. And they don't care what happens after the first 10 arrive. They're just going to wait 8 more seconds. So 1, 2, 3, 4, 5, 6, 7, and maybe it's really 7 seconds. I have to count it out. Oh no, I think it's 8. On the 8th second here, instead of number 4 being up here, number 4 is instead down here. And you notice everything has shifted down one spot. Do you see that? And now there is no more number 1. Where did it go? Out of the buffer and? Exactly, onto the screen. That's the job. The job of this buffer is to drain everything out. And so what happens over here is number 2 leaves. Everything shifts down. So I'm still adding packets on, but at the same time I'm removing packets from the bottom. So it's like Tetris. Everything pulls, pops out at the bottom. Right? So as long as I'm still receiving packets, then I can maintain my buffer. It never gets any smaller. At the end of this, there was another pause, but the playback has already begun. The playback cannot stop. It must continue now. If I run out of packets now, I have to stop the playback. That's the kiss of death. You don't want to do that in the connection. So I have a very short pause of only 1 second, and then the third packet starts to arrive. But because nothing arrived here, then my buffer became a little smaller. It's now no longer 12 bytes tall, now it's only 11 bytes tall. So if I receive the end, now I'm done receiving packets. Now all I have to do is to drain the buffer. And so now with every second, I drop out number 10 from the second packet and then number 1, number 2, number 3. They all start leaving. My packet gets smaller and smaller and smaller. And then finally at time 48 maybe, this is 46 right here, 47, 48. And at second 47, I think that's what you said, I spin the last one and I'm done. The columns are seconds. Time is passing. Oh, sorry, this is what's in the buffer. It's a LIFO buffer. So this is last in, and no, it's a FIFO buffer, first in, first out. So these are the last things to arrive. These were, back a time ago, these were the first things to arrive. And so they're the first ones out. You send me the first picture in the movie, that's the first thing I'm going to play. Then you send me the second picture in the movie, of course that's the second thing I'm going to play. I'm going to play them in the same order you send them to me. So this one works well. Plenty of buffer, plenty of packets, no problems with the delay. In fact, if I had one complaint about this, what might it be? Well, you have to be really careful about that. That's for sure. And so we don't show that here because TCP maybe takes care of that before we see it. This is an application layer protocol, but you absolutely also have to timestamp these because lots of these protocols ride on top of UDP because it's much faster. And so they don't have any one to check. So you will find these algorithms, they all timestamp and they all packet number everything that makes it across. So it's a good question. But what's a criticism that you could make of this implementation? Yeah, that's, or other ways of saying that same thing. It uses too much memory, which is the same thing as you let the buffer get too big, which is the same thing as saying what? What would the user see? How would this affect the user? Delay. You make them wait too long to start playing back the movie. So the homework problem is basically going to ask you, suppose instead of this 20-second overall, and you can't see that in the buffer, but I chose this because I need for the playback to begin within 20 seconds of the user asking for it. So what's involved in asking for it? Well, from the time you ask for it, you have to send the request, it has to arrive, and the packets have to start coming back. And you need this to happen in less than 20 seconds. Less than or equal to 20 seconds. Did we do it? Yes, we did. Here's 20 seconds right here. And we started playing back right here. So that worked great. Barely in time. All right, so we were able to do it. How long did it take for this to get there and back? Apparently it took one second. Because there's only 1 second from the time I began counting and the first packet arrived. So it's not far away. It's, you know, close. Maybe it goes out over different network. Who knows why? But I didn't want to waste a bunch of space with that. So that's 1 second round trip. So you ask for it here. It goes to the sender. You start receiving packets here. And you get 10 packets in a row. And then you get nervous for 5 seconds. And then you start to get more. And then you start playing back here. And the user starts seeing something before they give up, which is at 20 seconds. The algorithm will reboot. So the question I'm going to ask you in the homework is, what if instead of 20 seconds, it was 10? If you needed to start playing something back within 10 seconds, would it work? So what you're going to have to do in the homework is redraw this diagram, but only with the green packets. You do not have to redraw all this garbage. Yes. Yeah, you're going to have 3 sets of packets, 30 packets total, 10 in a window at a time. So 10 are sent, and they're sent in bursts. 10, and then right behind it, 10 more. But the network, if it's going to put any delay, it's going to put it between the 10th and the 1st. I could have made it a lot worse, but I kept it simple. All right, so there's only delay between here and here, and between here, and it's exactly the same delay. None of that changes. It's the same situation down below. You receive 10 packets, then there's 5 seconds of delay. Then you receive 10 more, then there's 1 second of delay, and then you receive the final 10, and that's it. You're done. So the only thing that's going to change is the shape of the graph. Do not draw any of this garbage down below. And I have no idea what I just did to my graph, but I totally screwed it up by messing around with my pen. So your answer is going to be something like, here's the first one. You know the second one's going to be here, and then the third one, and then the fourth, and then the fifth. And you're going to have to start replaying sooner. Yep.
So when it's stabilized, is when the user starts something on the screen?
Well, there's a different way to describe when you see it stabilize. Can you be any more specific? Yes, the user has started playing back, but it also... Exactly. You're receiving the same amount in at the same rate you're delivering to the user. So it's maintaining status quo. You're getting packets in, packets are leaving, but they stay the same. The other explanation for it being the same is you're not receiving anything, but you're not playing anything either. Right? So it's just sitting there waiting. That's what happened here. Right? You're not playing anything back, but you're not receiving anything either, so the buffer doesn't change size. Once you decide to start draining the buffer, it will never stop. It has to go all the way until it's empty. 1 packet per second. Drain, drain, just like clockwork. So if you do this too aggressively, you will run out of packets before you've played the 30th one.
Does this happen only on stream?
Yep. Yep.
So like this is...
Nope. Well, YouTube's a stream. So it absolutely, it happens all the time. This is exactly how YouTube works. So if you saw that you were running out of packets, let's say you set an alarm in your buffer and said, let me know if it ever gets down to 5 packets with the buffer left. They don't have to have the number 5 to be 5 left. You can count 1, 2, 3, 4, 5. There are 5 packets in the buffer right here. They don't happen to be numbered 1, 2, 3, 4, 5, but that doesn't matter. So if you ever get down to that point, send me a message and let me know you're running out. Because I'm still sending you packets. I'm assuming you're getting them. But if it starts to slow down and you're about to run out, tell me so I can start sending you smaller ones. and I compress them more. I use higher level compression and shrink the size so they have a better chance statistically of making it across the network. Smaller packets, it's like if you have a jar with boulders in it, you know, these red lava rocks that we always step on out here and hurt our feet all the time? Yeah, and for all of you that are throwing those out in the lawn, I want you to know how obsessive compulsive I am. Every single time I walk there, I grab a few and throw them back. So I'm on to you. You can keep throwing them, but I'm going to be here longer than you will, and I will put all those rocks back, just letting you know.
So making the packet smaller doesn't mean that resolution
exactly. Of course. Yeah. And you can see that in YouTube.
Yeah.
And you can see it on live Rayado streams.
Yeah.
You can see when it turns fuzzy and you can't read the writing anymore on the advertisements on the side. They've done that. And when the bandwidth looks like it's better, if the buffer starts to fill up, you might tell them, when you get to 80% full, tell me that too. So now I can start sending bigger packets again. Because obviously the network is, you know, you're accumulating a lot. Right? Yes? It's all done at the application layer. We did add a new protocol called RTC and RTCP that sit on top of UDP kind of in between, and they help, yeah, they help give you all of this, the streaming protocols, but you don't have to use them, but why not? Why not? RSCP is another one, right? There's a bunch. Yeah, so time 16 is actually right here, this little arrow. This begins, let me see if I can zoom this up a little bit. Time 16, too far. Wow, really? You're going to do this to me now? After all the work I've done to keep you running and happy? Okay, so this is the packet that's sent during second number 16. All right, so if I go to the top of this column, let's look. This is time 0, 1. No, I think I'd go with what you say. Let's call it 17. I'll make it clear in the homework to make it absolutely clear, but let's call this second number 1. You want to start counting at 1? Yeah, let's do that. 1, this is second 2. So I'm going to move these numbers over a little bit so they line up a little better, okay? So the 2 will be underneath this column. Deal? That'll make it clear. So back to your question. Whether it's 16 or 17, let's skip that. What we know is that the first packet gets played right here. Otherwise, 4 would have been on top. My packet would have gotten bigger. I was only accumulating packets up until here. No, my buffer size is not specified. It's variably large. It goes up and up and up. There's no limit to it right now. Yeah, so look at the bottom. Look what's happening at the bottom. Look, watch what happens. You see all the numbers in this column are shifted down, and there's no more packet 1. Packet 1 has left the buffer, and it's now being displayed on the screen. So the packet's been decoded. It's been converted into an image. It's been put into a frame buffer, and the CPU is busy rasterizing it on LEDs probably, right? And it'll do that, you know, 2-3 times with that frame buffer before it advances to the next one, because we'll refresh it 60 times a second, but we're probably only receiving packets 24 times a second. So let's go to YouTube. Yes. So what I'm saying is the way this algorithm works is if you do not start playing the video within 20 seconds of the time the user requested it, the algorithm will assume something terrible has happened and it will reboot. It'll give you an error message, it'll crash, whatever. So one thing I'm asking you to do is to redesign this so that it starts replaying within 10 seconds. So in order for you to do that, you're going to first have to figure out, is this going to cause me a problem? Is this going to make my buffer run out? You don't change any of this. It's still 5 seconds of delay and then 1 second of delay. So maybe it'll work out, but you have to figure that out. Right? So if I told you you had to start playing by second 10 right here, then you are going to have to start playing here. Maybe you could play here or here. You can pick whatever you want to do it. I may ask you, like, okay, how far can this go? I also may ask you, you chose to wait, sort of related to the 20 seconds, but independent. You also chose to wait 8 seconds after the 10th packet arrived before starting to replay. Now, you did that knowing that that would still keep you within 20 seconds, but you chose to wait 8 more seconds. So if I ask you, okay, could you have waited only 7? What about 6? What if you chose only to wait 5 seconds after the 10th packet? 4, 3, how far can you go? Do you have to wait at all? Can it be 0? So that's also what I'm going to ask you. So I'm nervous that it's tedious. That's why we're going over this together. If you can't do it, we'll just do it together in class. But it's fun, and do you see how many questions it made you guys ask? This is more questions than you've asked about anything else all semester. Am I right? So this is more interesting because this is stuff that you guys do. You're very likely to, have a project where you could write code to do something like this. So this is a lot like window buffering, but this is like TCP buffering, but where you care about it, like it's video streaming. So let's go look at YouTube, and I'm going to show you what we can do. Anybody got a favorite video that won't get me fired? Oh, this looks cool. Let's watch this. I'm like oh man, there's two that I want to see. Now there's planes taking off.
Hola y bienvenidos al máster en diseño digital con Adobe Photoshop CC.
Yeah, saltar. Okay. All right. So what I'm going to do is look at the quality, and we're going to drop it down. All right, nice peach, right? Let's switch the quality down. Can you see the difference yet? I can see it instantly, but I'm a party crasher. As my son once told me, every party has a pooper. That's why we invited you. Party pooper, party pooper, party. Do you know this phrase, party pooper? Okay, yeah, the little smart ass, yeah. But he got me back because until he was 4 years old, whenever he wanted to do something and I didn't want him to, I said, okay, let's toss a coin. Heads I win, tails you lose. And he goes, okay. And so I do it, and I go, oh, man, bad luck, Zach. So, and then one time when he was 4 years old and I did, he goes, hey! I went, finally, let the record reflect that on June the 3rd, 1998, you finally figured out that you're being had. You need to, be smart about that. It's going to happen your whole life. All right, so if I drop down another one to 144, look what this one looks like. Crappy, right? So let me see if I can back up a little bit. Okay, this is fantastic because you can actually see the JPEG quantization happening right here. Can you see this little square right here? Yeah, awesome. You can't often see that stuff. Of course, I had to screw it up by moving my cursor again. Now, if I shrink this down, you think it'll bother you as much? Can you still tell it's bad quality? What about if I do it down here? Can you see here? You can't see anything here now. What about if I do normal size? It's a little harder to tell here too. Okay, now that we're watching this, we kind of want to see what the heck's going on. Is he planning on what's he doing? Oh, he's landing. Okay. Well, that didn't go so well. Fired. Yeah. Dumbass. All right. And I'm sure that's what. Well, the thing you got to remember is that the landing pad is moving. Okay? You need to land over there, not land where it's going to be. It's like playing hockey. Skate to where the puck's going, not where it's at. Did they teach you this in soccer? Run to where the ball's going, not where it's at. Right? So if you want the ball to be somewhere, then All right, that wasn't the video that I thought. I didn't want to see anybody get hurt in that. Okay, so now we've all got it. So what's happening when you switch the quality is it's not slowing down the video. It's not getting jerky or anything. But what it's doing is sending you much smaller files that are much more heavily compressed. And you see the pixels got bigger. They got a lot larger, each pixel. So they still have to try to paint the screen, but they use a lot of math to try to smooth it so you don't notice it so much. Yes? Yeah, that will reduce the amount of space in the buffer that each packet takes. So that's a complication that we won't model in the homework. It's too hard, but absolutely. It's smaller when it's sent. So what you'll do, and what MPEG does, is they will look at the packets before, and they may look at the packets coming after. And if they see a big change coming, they'll start changing a little early, or they will make changes gradual. So they'll average things. They use every trick in the book you can think of. One of the things you can do with interpolation, which is the name given for the class of algorithms where you're trying to reduce what you send, is you will look at the you'll look at the pixels around you, and if they're close enough to you, just don't send you. Just say fill in the blank, figure it out, and you'll do that as well. So you try everything you can to not send data and to compress as much as you can. Okay, yeah.
And what happens if you set the resolution to 4K, but you have a screen of HD?
So that's called transcoding, and that's happening right now in WebEx, because I'm sending you and it happens in the reverse as well. If you only send it a 1080, but you have a 4K screen, you know, what are you going to do? Are you only going to fill the middle part of the screen, or do you want to see? So people usually expect you to fill the whole thing. So this is called transcoding, where you will bring something in, you will put it in a frame buffer in memory, so that the whole thing is full, and then you will recapture, recompress, and re-image it on the fly from that frame buffer as if that had been the camera sending it directly to you without any of that other stuff ever happening. So you just start over with that as your image. And you can't really tell how many times that happens along a connection, but you can see that it degrades. So what happens with WebEx is, if I'm in a room with a very high-end system called telepresence, have you guys heard of this before? They use it sometimes on TV shows. They use it in 48 hours, and you know, this is one of these things where Cisco will pay people money to use these systems. Let's see if we can find a picture of it. So this is a typical telepresence room. These have just enormously high-resolution cameras. The rooms are engineered by acoustics engineers and everything else. Everything from the color of the paint to the decibel reduction of the ceiling tiles and the carpet, the number of inches away from the screens, all that stuff's engineered. It's all completely figured out. And this camera is capturing very high resolution. But you can listen in on one of these things from your phone. And you can see what's going on your phone as well. You will only see one of the screens instead of all three of them, but that's got to be downsampled, transcoded down to a much lower audio rate, a much lower video rate. And if you leave Wi-Fi and you get to the cellular network, the bridge is like, God, will you sit still? Because it's got to change it again on the fly. So those bridges are doing tons of transcoding for all different users. So when YouTube is doing something live and they have YouTube Live, they're probably sending out, I don't know, 500 different combinations of compression, frame rate, and pixel size, and window size, just to support all the platforms that are, you know, going on right there. So it's hard. You can see it, but if your screen's smaller, you can't. You won't notice the difference. So that's what they try to do. So YouTube's one of the few sites that make this a little bit easier on me by exactly allowing you to pick resolutions. Yep. When you've had me for 2 years, you can start to finish my sentences, which is actually really, really cool. Oh, yeah. Is it really? I didn't know that. Well, I've seen you around before. Then maybe that's why. Really? I don't know. I didn't say I talked to you. I said I've seen you around. Yeah, that's exactly right. So go for that, right? Why not? That's be noticed. What's wrong with that? That's what you want to strive for. All right. So we good on this for now? Is that we beat that to death for a minute? Okay. So let me quit out of this. I cautiously want to save it, even though I'm not sure I really want to. And so we have 2 things to go over, and I don't know that we'll get through all of them, but I'm going to start with mobile IP because I think I can get through that one faster. So mobile IP, we may have talked about it a little bit before in prior classes, but it's not something I'm going to talk about because you're going to be using it every day, but the things that it innovated are used every day. You use what mobile IP figured out all the time. So it's as good a model as any to kind of discuss what happens when people start moving around on the internet, carrying their laptop with them, their IP address is changing, they expect their apps to continue to respond to them, they expect DNS entries to get updated like by magic somehow. So these things were first tackled before laptops were around, when we had slightly larger machines. I used to go to conferences all the time with Stan Barber. He and I worked for the same person, and Stan ended up running Google Fiber, and now he's doing some other Google research thing. But we went to the same school, and he's like a super big shot. And so I got to have dinner with him, and it's kind of fun, like to have a friend who's like kind of in a cool spot. And then I have another guy I went to school with who's the CFO of Level 3, which is now got changed names to CenturyTel, something like that. And he remained in that job. So he's the chief financial officer for like 80% of the fiber in the world that runs the world's internet. So that's pretty cool. And I had lunch with Steve Jobs once, but that's my claim to fame. All right, so mobile IP was done back in an era when I used to hang out with Stan all the time. We worked together, and we would go to conferences and things, and you'd bring sort of a machine with you. You'd check it in as luggage. It would be like a Sun Spark server. It was a pizza box, they called it. It fit into a rack, but you could also use it, and we'd borrow someone's monitor or figure out how to hook it up to the television in the room. And Stan rewired. I mean, God, I can only imagine the amount of money he cost hotels, because the first thing he would do is start ripping the jacks off the wall and rewiring the jacks because they never had them wired exactly right to spec. And I work for the phone company. I'm like, okay, whatever you want to do. And he'd rewire the television and unhook all their security stuff, and it was a lot of fun, especially since it wasn't me and I wasn't going to get arrested no matter what happened. So he was fun at doing that stuff, and we would then try to connect back via a modem to dial back to home base. But the next day when we showed up at another university and we were working there, we would ask for connection. And that's when the trouble began, because there was no DHCP, and you weren't known to the network, so BootP wasn't going to really work. So you couldn't get an IP address by just showing up. There was no Wi-Fi. It hadn't been invented yet. There was no wireless at all. And so you would plug into Ethernet, and somebody would have to come around and add an IP address and a subnet mask manually to a configuration file in /etc/lib, config dot, whatever it was. And then you could get on. And then back home, nobody knew that you'd moved, and so you had to log in with remote shell and try to update some tables, so people that were trying to telnet to your name would now find you at the new location. It was hard. And so when you showed up to do trade shows and you needed to bring demo equipment to show a program running on the internet, it was you had to bring the network guy with you. It was a big deal. It's not like it is now. So mobile IP was there to try to solve a lot of these problems, and it was successful. It did it. So we'll talk about sort of how we did it. So the main problem is addressing. The first thing you need when you move someplace else is you've got to have an IP address. And if you're a moving target, then it's doubly trouble, because IP was never designed to handle moving targets. It was designed to have somebody sit behind a router on your subnet with your subnet mask, minding your own business and sending your little packets out to the internet, right? And that's exactly what we do not want to do. So mobile hosts, one thing you can do to solve them is invent DHCP. You show up at a new place, you see that you don't have an IP address, you broadcast a DHCP packet, you hope, cross your fingers that someone answers. Most of the time they do. At any kind of business with open Wi-Fi, they'll do that. They may not let you get onto the internet, but at least they'll give you an IP address, so then they can ask you for money or to give your email address or to see what your credentials are. If it's Infinitum Mobile, for example, you're going to be asked to log in. But the drawback of getting DHCP is it requires maybe rebooting, not these days, but that was a big issue back then. It absolutely required rebooting. It may require changing config files if you had to change your address. I just talked about editing that. The DNS table must be changed so everybody knows you're not at the old IP address, now you're at the new one. And that can take an hour to propagate, so nobody may know where you are. In fact, if you sign up for a website and you buy a domain name from GoDaddy, they'll tell you it may take 24 hours before this works, because it may take that long for DNS servers to update their entries and for anybody to say they know who you are. In my experience, it's never taken more than about 60 seconds, ever, no matter where I am when I create a domain name. And you can sign up for them. They're cheap. $5 you can sign up for them. And if roaming happens, God forbid, if you change IP addresses in the middle of a TCP session, after the handshake, in the middle of a window, that's like indescribably difficult back in that time. We didn't have any idea. It's just like, well, you're just asking for trouble. You deserve to have all your connections dropped. So now what happens? You're streaming Rayados, and you're in your car, and you're going from one cell tower to the next, to the next, to the next. Does it make you re-log in, everyone? No, there's two things happening. One is, if you're staying with the same carrier, they are maintaining the super subnet that doesn't change one cell tower to the next. So all they're doing with the tower is providing you a layer 2 connection. They intentionally do not make it layer 3. So wherever your IP address is coming from, it's not from the tower, it's coming from some router back in the bowels of their network in downtown Monterey. So any tower, they all use the same router to assign IP addresses, and so you can move from any tower you want, and it's never going to change your IP address. That's the way mesh networks work on campus. The reason why you don't drop your tech connection when you walk down the hall, if you've ever tried doing, well, but that's because you walk away too far away from a hotspot. But you can move from one Wi-Fi hotspot to another. Maybe in the library would be a better example, where it's denser, because they built a layer 2 mesh. So your IP address doesn't have to change, nor does the SSID. It's still tech the whole time. So they create a layer 1 mesh, basically layer 1.5. So you want to not push layer 3 out too far. This is one reason why network managers buy lots of switches instead of routers, because switches make these things easier to implement. But we didn't have any idea how to do it at the time. All right, so what if you take a look at options? What if instead of trying to change everything we know about you, the DNS and all this other crap, why don't we just give you a second address? We'll let you keep your old one at home, and if people try to send something to that old address, it will still be there. It's still part of the network. The world thinks still that that's where you are. You don't have to change anyone's routing tables. Everybody will still send packets that belong to that IP address to the same router they always have back at home. So how's this going to work? Well, if I give you a second address, maybe it's like a loaner address, a temporary address that you get from wherever you are at the moment. And you're going to need to invent a protocol between the two routers at these sites. And the way this scheme is going to work is you're going to tell the router back home, I'm stepping away for a moment. Please answer my calls for me. It would be like a secretary. I'm not going to be here for a while. If my phone rings, will you please answer it? If I receive a packet, will you please receive it? Well, what do you want me to do with it? Well, not much, because I still want you to send it to me. So I'm going to tell you where I am. When I get there, I'm going to tell you, okay, I'm downtown, and here's my phone number where you can reach me. So if I get any calls, please just forward the call over there. There was a Woody Allen movie where an actor played this extremely busy psychoanalyst, and he was, constantly moving around town. So he would call his answering service, and he'd say, between 1 and 1:15, I'm going to be at the following number, and then from 1:15 to 1:20, I'm going to be on this number, and then you can reach me from 1:40 to 1:55 at this place, and it was just ridiculous, right? So it was supposed to be a comedy skit, but I remembered it because, I was working at the phone company, and I'm like, oh, wow, is that how people do that? So that's what this software does, is when you move around, you tell it where you're going to be. So we have a concept of a original home. You have your home network. There's a foreign network where you're visiting now. You're going to be given a care of address and a home address. So has anybody ever had to send something to someone in the military, by any chance? Well, because of the United States, it happens a lot more often. We're in a lot of wars, a lot of times. So there's this concept called an APO, and if you've ever seen an address with an APO, that basically stands for a special type of address, where if you are in a military unit and you're over somewhere in Afghanistan, they're not going to let you tell them where you are. Mom, I'm at this little hut on this street in Kandahar. Well, there's obvious reasons why you don't want to tell people where you are, but you also could be moved at any moment. So what they do is they set up a care of post office in Brandenburg, Germany, let's say. So all of your packages and your mail will be sent there. And periodically, the postmaster, when there's a flight with supplies going to wherever you are, they will put a box of all the mail and packages in there. So it may take a month to get your mail, but you'll get it. You'll always get it. And what Mom sends packages to is this APO. So it gets sent there, and then that gets forwarded on to wherever you really are. It's the same idea. They think you're there, but it'll get forwarded to wherever you are. So this person and this person have to know what's going on, but this person does not. All right, so that's important to this scheme working. So it's very much like how VPN works. You can be anywhere. In fact, when you get to the end of this, you will see this is exactly where VPN comes from. That's why we're teaching this. That's one of the many things that came out of this. Is a version of this is what you and I now call VPNs. All right, so they solved this concept. So addressing a mobile IP, you need one address for your home address and one for your care of address. So now we're in this mode where I'm with Stan, we're at a hotel, we want to get this PC working at someone's thing, and so we got to dial somehow, we got to get an IP address and then tell Baylor where we work or tell Rice this is where we are now. The home address never changes. That's where everybody thinks you are. That's where Mom is going to send the packages. And so the router there has to recognize what's going on and forward things to you. So you're going to have software to do this, and they're called agents. You'll have a home agent and a foreign agent. It's just a program that's running on a router. So it's yet another block of code that's going to run at the IP layer inside your program. It can be an application layer protocol as well. It's not terribly important where you run it. It just has to be run. It's like DHCP. If you decide you want the router to answer, you have to run DHCP on the router. If you want the router to answer DNS queries, you have to run DNS on the router. So these routers are really Unix servers. They run Red Hat Linux. Anybody see who bought Red Hat today? IBM. IBM bought Red Hat. Yeah, that's a lot of money. For a company that only makes $4 to $6 billion a year, and they own absolutely nothing. They have no intellectual property. The software, they don't own. The Unix that you use, that you get from them, doesn't belong to them. They don't technically sell you a license for the software because they don't own it. The Open Software Foundation owns it. What Red Hat does is sells you support. That's all they do. is they will they establish an 800 number, a place for you to call when Unix isn't working, when open software Unix isn't working. You can call them, and they will fix it. They'll find the problem. They'll work with you, and they'll write the patch, and then they must publish it back to the Open Software Foundation immediately. Yeah, it's Red Hat Linux, but they don't own the Linux. We spend $30 million a year with them because that's their stuff that runs in all of our routers and switches. So I licensed that for everything we did, and worked really, really, really closely with those guys for a good solid year. And they had some really crazy good engineers, just like mind-numbing how good these guys were. And they couldn't hold on to them because they were so good. They go out and talk to customers, and the customer's like, okay, how much do you want? You know, it's like a big bank. I remember being in Berlin with this one guy, and we went and talked to the bank, and he just like vanished after that. It's like, how much is it going to take? You know, and there's a story about Bill Gates when he was trying to hire a guy, I want to say from Symantec maybe, or something like that. He's trying to buy their software to add virus protection to Windows. This would have been 20 years ago. And he offered the guy, I don't know, $2 million, $3 million or something insane to come over and then give him a big job and all this other stuff. And so Bill calls him on Sunday night, and you know, he says, so what do you think? What's your decision? And after 5 minutes of hemming and hawing, you know, the guy basically said, I can't do it. And he goes, well, that's too bad because I was calling to offer you another $3 million. And he goes, can I start on Monday? You know, so it's all about how much at some point. So there's crazy money sometimes that gets thrown around on these things. But yeah, Red Hat got bought by IBM today for a lot of money. So this is basically a Unix machine running Red Hat. That's what a Cisco or any other router generally is. So you have the ability to run other software on here, a home agent and a foreign agent. You just would like for it not to have many bugs, so people can't get access to the OS and mess with your router. So when the mobile host, the guy that's running around, you or me, with our laptop, and the foreign agent, the software that's running in the router, when these are the same thing, you can actually run this software, foreign agent software, inside your own mobile host. You don't have to have help from another computer like this router to do it. So when you run them together on the same machine, it's said to be co-located. So that's what a VPN does. Is the VPN handles everything. You don't need help from the router to open a VPN connection. You have all the software you need on your own machine. All right, so there's 3 phases of building this thing up. You go through agent discovery. When you arrive at your new location, you send out a probe that says, hey, anybody here speak mobile IP? And if there's a router that does, they will answer you. We've seen this a lot of times. You send out requests, you broadcast them out for lots of different protocols, and then you get an answer back. Right? So this is another one. That's nothing new there. So we're starting to see more protocols, and we're starting to see kind of habits. So you guys would be able to kind of make educated guesses on how to do one. There's registration where you basically say, here's who I am. Will you please tell my home agent that I'm alive, I'm okay, and please start sending me my packets again. And then you have data transfer. So the first phase, agent discovery, involves, oops, scroll too fast. The mobile host, that's the laptop. The foreign agent, that's the server near you. And the home agent, that's your home router. And the second phase also involves those. The third phase is just the remote host. So we're going to look at each of these a little bit more in detail. So nothing like a graph to kind of show what's going on here. Your mobile host, when you're at home, you basically tell the home agent, I'm back, I made it back, stop forwarding my stuff, I've returned home again. He goes, thanks, because I was getting really tired of opening your envelopes. So here's your junk. When you leave, however, when you move, then you show up unannounced at some foreign agent network. And this person wasn't expecting you, and this person doesn't know where you've gone. So you need to send out a broadcast saying, is there anybody here who speaks mobile IP? Yes. Will you please let my home agent know that I'm okay and here I am and here's all the details. So it contacts the home agent. Hey, one of your guys is over here. Like, I found your dog on the street. He's at my house. He's fine. I'll feed him, but you might want to come and get him later. I mean, or it's like your kid was still playing in the yard with my kid when it got dark, so I brought him in and fed him dinner. I hope that's okay. They're having tacos. Yeah, that's fine. Sorry about that. Thank you. Right? So registration reply is, yep, that's okay. And the foreign agent says, okay, your mom says you can stay a while. That's cool. And then now there's data transfer, but the data transfer is with a new device that we haven't seen yet, the remote host. The remote host is nothing to do with mobile IP. The remote host is basically the person that was trying to reach you. So this is just some random internet user. They are not a part of any of this. They don't run any of the software. They have no idea what mobile IP is or agents or any of this stuff. All they tried to do was send you a packet. That's all they did. They're out on the internet. They tried to send a packet to your IP address. And if you've made it through all of this, then you're reachable. They can get something to you. So the book has a couple of flaws in the way they sketch this out that we'll get to. So if you're sort of seeing contradictions here, wait a minute until we get, and you can still tell me if you got questions. So mobile IP doesn't use a new type of message. It actually piggybacks on an ICMP message that we've already seen, the router advertisement packet. So they just shoehorned it in perfectly fine. It's actually kind of a clever idea to just use an existing ICMP message. So all they basically do is put a router advertisement out there. They set the type field and they set the sequence number, the lifetime, and then the caret of address is a list of available addresses that you can use. So this is what comes back from the router that says, oh, welcome, glad you're here. You need an IP address, I assume. Here's a list to choose from once you pick one. And so it will choose one and then register back and say, you know, I'd like to use this IP address if that's okay. So you have some codes that are set. Very often registration isn't required, but you've got messages that kind of help you understand what the router is capable of. Is he willing to be a home agent? Is he willing to be a foreign agent, etc.? So you can go through some of that stuff. And then it also doesn't use a new packet type for agent solicitation. It'll use the same one for that as well. All right, then you need to register. Once you know the host is there, you've got to register. You basically found somebody that's willing to forward packets to you at the local network. Now you need to let your home network that you're here. So you'll register yourself with the foreign agent. We just did that. You're in a new place. You told the router you're there. The mobile host now must ask the foreign agent to let the home agent know, I've moved. Here's where I ended up. You know, you told me to call you when I got there. I'm calling you, I got there. And you're going to periodically have to renew your registration so it expires. And then you're supposed to deregister when you get back home. And we already saw that in the previous diagram. So registration request is a message that's sent. We saw that in the diagram already. The foreign agent will relay that message and then gives you the answer back. So here's what that protocol looks like. We don't need to know this in detail. What you should be absorbing from here is how this is very similar. Pattern matching, like, okay, this doesn't sound any different than the last 5 protocols I've shown. And that's good if you're starting to see the patterns. So you have a home address, home agent, care of agent, and I may ask you a homework question with a little bit of detail in here. It's not hard to figure out, and you can kind of step through it easily. This is a lot like an ARP request. Fill in what you know, leave blank what you don't know, and broadcast it out and see if somebody will answer and fill in the blanks. That's basically the idea. Okay, let's see if we've got anything else that I want to talk about in here. I don't really think in this part. Okay, then encapsulation. So registration messages are part of UDP, so this is running at the application layer. They use a well-known port, 434, and routers are going to run mobile IP on there if they want. All right, so now you've got it registered. Now it's actually time to send data, and this is where the book starts to make little mistakes. Okay, so the first thing is we got to get the nomenclature right. This is a remote host. This person has nothing to do with mobile IP. Okay, half of you will mess that up. So I will say it again. This remote host is just some random internet user. All they're trying to do is send you a packet. You could be the New York Times, and this person is just trying to open up a connection to you. You could be running a new little texting app that you're testing, and you got yourself a little domain name, and you parked it on your laptop, and you've got a DNS host that's going to keep track of you. You know, Skype, remember we talked last time, every time you move to a new IP address, Skype sees that and tells Skype, hey, this guy's moved, he's over here now. And your light turns green again for everybody that's got you in their directory. So this is, you know, you can move around, something like that. And so this host doesn't know any of that. All he's trying to do is connect. So this is, they have no special software. They're not going to do anything special because you're on mobile IP. They're not impressed. Right? They don't care. So they are just going to send a packet, and the internet is going to forward that packet the way it would have forwarded any time during the day. It sends it to the router that has that subnet. So if this was an address at tech, of course it's going to show up at a tech router at the edge of the network. And then, because that's what the world's routing tables told it. And then now you're going to have a problem. The home agent's got to figure out, okay, this is one of those IP addresses where this guy likes to move around a lot. Is he home or is he away right now? Well, I look at my mobile IP table, and he says that he's away. And in fact, he's checked in, so I know where he is. So the next thing I need to do is send him this packet. This user got a packet to him. Now I want to send it to wherever he is. So I'm going to forward the packet, but I'm going to do it through a tunnel, and we'll talk about why. So it shows up at this foreign network. The tunnel actually runs all the way end to end. And so the packet pops out over here at the other foreign agent, and the foreign agent can now drop it on the local LAN, and you will get it. So that assumes that the foreign agent is going to change the IP address from the one that you really have to the one that you're currently using. Because if he drops a packet on this network that has this address over here that you used to have, what will happen to that packet? Well, it's never going to get to your laptop, that's for sure. It's either going to turn right around and go, oh, how did that get here? That doesn't belong here. Let me forward it over the internet and send it back. Or more likely these days, it will get dropped, and a little intruder alert alarm will go off. That is not where you should have seen that address. So it'll cause a problem. So that's gotten a little more complicated. So what we probably need to do is extend the tunnel all the way to the laptop. That's what a VPN does. Right? Why is this tunnel here in the middle? Well, this tunnel here is because we also can't forward this packet that's got your address here over the internet. If anybody along the internet sees it, they're going to do the same thing. They're either going to reverse it or drop it. So we have to hide it. So we're going to bury it in a tunnel. In the beginning, it was a tunnel called a GRE tunnel. That was one type of tunnel. Other tunnels are like L2TP, Layer 2 Transfer Protocol. There's a bunch of different tunnels. They don't necessarily do encryption, but they just hide what's going on. It's like putting it in another envelope and sending it off. It's like Halloween costumes that we'll see in the U.S. tomorrow. You can't really tell who's inside because they're tunneled. You can take the tunnel off and see who it is, but that's what the kids want to do. They want to disguise who they are from you. Yeah. Yep. It's why does it stop early?
No, what is that?
Why did I say this is not for the internet? The tunnel does run over the internet. I don't remember exactly what I said, but let me make sure I don't confuse you. Nobody here has to know anything about mobile IP. They don't have to know anything about tunneling. Everybody in the middle is just forwarding datagrams. You drop something into a tunnel here and send it out on the internet with this guy's address. It shows up at the other end. He knows to look inside and he will find an IP datagram that was last seen over here. So it's like you've connected these two networks together with this tunnel. What you pour in this into the tunnel pops out at the other end, just like Lomas, right? Just like in Monterrey. What drives in one side pops out the other. But nobody here knows anything, and this user absolutely has no clue what's going on. Okay, so I've gotten the packet. Let's say it was an HTTP request, and you're running a little web server on your laptop. So this packet got to where it should have gone. It was forwarded over to the foreign agent. The foreign agent got your laptop, and now it's time for the laptop to respond back to the originator. So he's going to send a response. Let's say he sends a web page. So he's going to send an HTTP packet. It's going to sit on top of TCP. And if you follow the arrow in number 4, I don't know how that works, because the source address is going to come from this subnet, not this one. And this guy has no idea who this is. He'd never asked for a connection with this subnet. He never did a handshake with this subnet. He thinks all the traffic is going to somebody over here. So he has a TCP connection over here. Maybe you can forward that over here. Okay, maybe you can forward it, but it still has to have the same IP address, or this guy's going to get confused. So what's this? How is this supposed to be a direct path? Yeah, it's shorter, but I know of no way to make this work without sending it all the way back home and all the way back over to the remote host. You have to reverse your steps, just like, by the way, a VPN does. A VPN goes, every packet goes all the way back. So if you open a VPN connection from your laptop to Cisco, and you use your laptop, now that it's connected to Cisco, to send a packet to your computer sitting here in this classroom in Aulas Tres, even though we're 3 feet apart from each other, the packet path has to go all the way out to Cisco and back. Every single packet goes all the way there and back. This is how WebEx is working. I'm sending all my WebEx packets all the way back to Richardson, Texas, and if all of you were on WebEx, they would all be coming all the way from Richardson, Texas, all the way back. Even though it's very inefficient. Reason why is because it works. We don't lose our minds. We can debug it. We can figure out what's going on. We can understand. Yes, it uses a lot more bandwidth, so just suck it up and buy more bandwidth. Sign here, press hard, make 3 copies. That's the joke we used to say. That was our job, is to tell people the answer to all of your problems is always buy bigger network. You need to buy more network. Well, it's hard for me to get the backup time. You probably need to buy more network. And we can't get the ATM thing to work. The network seems slow here. You probably need to buy a bigger network. We're thinking of opening up a data center over here. You need to buy a bigger network. No matter what your problem was, you needed to buy it. And that's a valid strategy lots of times. That's what this drove. It sucked up a lot of network bandwidth. Okay, so inefficiency is you can have double crossing. That's what we just talked about. You and I are in the same room. That's inefficient to go all the way back and forth, but that's exactly what you need to do. It's too hard otherwise to figure this stuff out. Another one is triangle routing, where you send something to a home agent, it gets forwarded all the way over to me. Gee, wouldn't it be easier just to send it directly to me? Well, that's a variation of what we just talked about. So, no, it would not be easier. This says it's inefficient. I would tell you it's impossible also. So you can't do that. You need to go all the way back home. I don't care that it's inefficient. You'll never get it to work. You will never get router operators to agree to do this for you any other way. You have to tunnel it yourself all the way back to some place that you also have control of, and then they can send it for you there. Right? That's the only way to get it done. All right. So that's what mobile IP is in a nutshell. And you guys remember the flaw here is I really don't know how to get this to work. So I have a tunnel. The tunnel needs to go between the two. If I combine all the software into one, then the router, even this router, doesn't need to know what's going on. Certainly none of the routers on the internet have any clue what's going on. They're just forwarding packets. So you can make this guy ignorant as well and just extend the tunnel all the way to your host. Don't give the router anything to do. Extend the tunnel. So if you extend the tunnel all the way to your host, your IP address changes. Do you believe this? Have you seen this happen? Do you want to see it happen? Do you want to see that happen? Let's go to a site, whatsmyip.org. Okay, it tells me this is my IP address. Okay, first checking, make sure my phone's not plugged in. Because, like, first of all, I would, oh, what's that IP address? So where does that IP address come from? So this is a website. All it does is it builds a web page, and at the top of it, it writes out the source IP address of the packet that you sent your HTTP request. So you open up a web page to whatsmyip.org. It does a TCP handshake. Then it sends an HTTP GET request for getindex.html from this site. And the web server is actually a little program that's running. It looks at the HTTP request. It sees the IP address it's coming from. It builds this web page. Of course, it puts ads on it because that's how they pay for this. And then they show you your IP address. But they also show you stuff they got out of the HTTP request. Because we blab a lot. We give a lot of stuff to web servers. We tell them what browser we're running, the version number. We tell them the platform that we're on, what version of OS we're running. All that stuff, we voluntarily give that when we try to make an HTTP connection. Why do we give all this information to a web server? Why do we do that? Well, the IP address is enough to tell you where you are, but you're on the right track. They need to know this stuff. Why? Do you think if I open this web page on my phone, it would look the same? Why not? Ah, so how does it know to give me the mobile version? Because of this stuff right here. The stuff that I told it when I made my HTTP connection. So let's say I go to whatsmyip.org here. And depending on the browser type, well, it thinks it knows where you are. I don't know if anybody can see this. Let me see if I can make this bigger. Can I make it bigger? I think I can make it bigger if I stop sharing. And then I pick me. Can I do this? No, there's a way. Does anybody remember? I want to do that. Yeah, that didn't help much.
Three dots.
I thought so too. Where? Donde aquí?
The left upper.
Oh, that tells you the meeting info.
Did you see what's a button?
There's no icon in the corner of the, yeah.
Well, this will shrink it though. This will make me go away. Yeah.
Oh, what's a button like of the layout?
I think somebody else has to be joining. My camera is on. And look, it's tantalizing me. I see a faint, giant version of me in the background back here. Oh, yeah, let's just do that. Oh, thank you. So back to sharing the screen again, eh? All right, so here's Photo Booth app. And okay. So it looks similar, but not totally the same. But not totally different either.
It's mirrored.
It's what?
Mirrored.
You mean the same?
No, I mean like when you see effect, when you put it like in the
Once you take the picture, I think it's flipped to,
Yeah.
I mean, I think it's not that.
Oh, that's what you're talking about. It's reversed. Yeah, well, if you ever get a sales job, you'll learn how to read things upside down. Maybe that'll help. Well, like when the contract is in front of the customer, you want to be able to read it and show them, okay, you sign here and here without having to turn it around. So. Absolutely. Absolutely. Right to left, bottom to top. Yeah, you bet you do. If you want to get paid, you do. So, okay, so we got all this junk on here. So I'm going to open up a VPN now. Yes. Yeah. Uh-huh.
One is like 30.9 and the other one is 30.32.
So why is that? Where are these IP addresses coming from, first of all? Who owns that IP address? Hopefully. Do you want to find out for sure? Yeah, but you can also say things like, who owns IP 131.178.208.95? And see if you can find it there. Okay. Did it say? They did? Let's see if we can find it. So we got it out of LACNIC, which is what we expect, the Latin American Caribbean Network Information Center, and it's assigned to this company, Instituto Tecnológico, with a question mark in the middle. Gee, what does that mean? Yeah, get out. So that's us, for sure. And so why is the IP address changing from one window to the next? So when are you being assigned this IP address? When you connect to what part of the network? When you connect here? So if I go and look at my own IP address, what does this thing show me my IP address is? A net 10 address.
Yeah.
So when did it get changed to 131.178? Yeah. Does anybody remember the name of the process that does this? NAT. Network Address Translation. So every time you open a connection, you're assigned an available address for a little while. You open two windows to two different sites. Those are two different TCP connections. You got two different IP addresses. You won't always, but you did. Okay, so now what I want to do is open up a tunnel to a company called EncryptMe. And that's going to disrupt the WebEx. For a minute, now it's back. And so now if I go back over to Red again, and now if I say this again, now it's totally different. It's not 131 anymore. Do you see that? Now it's 143. Who owns that window? 143, it's a company called hostdime.com. Who is hostdime.com? Gustavo Salazar. That's the guy. He's Mexican. And he runs his place. So this company, EncryptMe, has one of their concentrators in Mexico at this guy's website in Guadalajara. He has a little data center and he sells hosting. So my packets are now going from here to Guadalajara, and now they're being put on the internet there. So I have an encrypted tunnel between my laptop and this guy's data center in Guadalajara. Cool, huh? So the IP address is assigned by him, by Gustavo. And where do I find Gustavo's name here? Well, why did I not see Gustavo's name? Maybe if I look this up, I'll find it. Wow, they took his name out. The overall company is in Orlando for DimeHost, or HostDime, but they have one in Guadalajara. What happened to, here we go, LACNIC responsible, Gustavo Salazar. Okay, so I'll turn off my tunnel. I think we can take a break because we finished with this, and what I want to talk about when we come back is fly through UDP and then get deeper into TCP. Does anybody know off the top of their head how many more weeks we have? Is it like 3? 4? Is it 4 more counting today or after today?
No, 4 because we don't have, the last Monday is a holiday.
Asueto.
We have classes this weekend.
Okay. 4 so Asueto and okay, that makes sense. No, Wednesday, Thursday. Yeah, and then the last day of class is like Wednesday or something. Right? Doesn't that sound right? I have class every day. For this course, I have class Tuesday, Wednesday, Thursday.
Oh, no, it's 3 weeks.
So today is October the 30th. So we have November 6th, the 13th, and the 20th. And the last day of class is the 21st. 3 Wednesdays from now. And then our exam, I have it reversed, by the way, and I need to send an email. I keep forgetting. We have our exam when the school schedule says we have our exam. And what I put in the slide, I have the Tuesday and Thursday backwards. The date and the time that belong to you are shown for the Thursday class and not the Tuesday. But if you have the school schedule, it's correct. That's when we'll have it. All I did was flip to them. Our final, there's 2 sections sitting in this room together. One of them has its final on the 29th. Maybe the other one does too. I just need to send an email out and make sure I get it right. Well, for this time, yeah, then that's when it is. All right. It's only the 3rd part of the class. Are you kidding? I'd kill myself trying to write an exam like that. There's so much stuff how would you study it? I mean, you know, I'm not everybody. I'm like different, you know. So, yeah, my job is to teach you guys, not to trick you guys. I mean, which is it? Are we teaching or tricking? So, I want you to absorb it.
I don't understand why many of the teachers here in Tech, which is the best university of Mexico,
Tradition.
tradition.
Yep, tradition. That's why we do it. And everybody does it that way. It's not just Tech. Everyone does that. It's like old-fashioned.
Everyone in Mexico.
Yeah,
But not in other countries.
maybe not. But in some countries, it's weird in different ways. So in some countries, all they want you to do is memorize and regurgitate, and that's it. They don't ever want you to think about stuff and figure things out. Let me turn off sharing internet. See, it already took over my connection. I caught it in the act. God, I can't believe that. A little jerk. Like stole my internet. All right, so let's take a break, and let's get started back up and plow through UDP and TCP. Sound good? All right, let me pause the recording. Get started again. So let's dive into a little bit of UDP. We've got about 40 slides, and I think we may be able to plow through this. We've seen a bunch of UDP already, so we're not going to have to really start from scratch on any of this. But we're going to go a little bit further into details to show things like muxing and checksum calculation, and basically to really nail down how simple it really is. So let me close this and get it out of the way here. Okay, so this shows, as we all know, that UDP is a peer of TCP, and we know it's a peer of the streaming protocol because we've seen almost all of these boxes in here now. We haven't looked at TFTP, but those are not used all that much anymore for things that users like us normally would poke at. So packets have a fixed header size. They're very, very small headers. It's a total of 8 bytes, which is crazy compared to IP, which is 20 to 60. So this is just very little bit on top of it. And it's got port numbers, a length, and a checksum, and that's it. So you can find decoders, decent decoders that will let you dump in stuff and decode what's going on. Wireshark will do it for you as well. So if I open up Wireshark and I just grab a packet or two, it'll do it. Come on. Ethernet, there we go. So I look for UDP. Okay, so I ran for 5 seconds and therefore there's 6,000 packets. That's typical. If I open one of these and look at it, that's all that's in there. Source and destination port number, the length, and the checksum. So the checksum's unverified, so if I want to verify it, there's an option in here. Try validate the checksum if possible. So it says checksum is incorrect, may be caused by UDP checksum offload. So what's UDP checksum offload? Is if you don't care, if you don't want the packet to even bother trying to do it, you can just say don't bother calculating it. And that's done. That's a way to speed them up further. The only thing doing a checksum does is slow the packet down. It takes a minute to calculate it, and you change the packet and then send it on its way. So it's a good idea if you're going to do this, unless you know that you need to validate it, just leave it turned off. Okay, you also can find a little bit in here about what direction things are in. And so the way we'll do that, since the packet is from a well-known port number, it's from a server. Well, that's cheating. That's not really what it was asking. So it doesn't really tell you. You just have to deduce from looking at the port numbers. If it's coming from port 80, you know it's coming from a server. Okay. And then the client process is the daytime client. So has anybody heard of that one before? Daytime UDP client. Let's see what this one does. It basically tells you how to do a daytime client. It's too much detail. I don't want that much. Yep, and then you can have a server. So this basically is to find out what time it is, essentially. Not very long code. You can write stuff in C or Java in this case. Try 3 times. It sits on top of UDP. Print out the length, print out the variation, so you can have a little bit of fun, simple things like that. All they did was go look up the port number to see who was using it. Okay, general services. Here is a list of the better known ports. Daytime is right there with one of them. Chairgen just parrots things back, returns a string. DNS, bootp, etc. So DNS doesn't always run on top of TCP or UDP. It will switch back and forth between the two depending on the importance of it. So if you send something that's too big to fit in one frame, it'll use TCP to do it, so it can keep track of order in Windows. If it's an update to a DNS table, that will usually go over TCP to add the sequence numbers and therefore improve the authentication. So fits in basically here. 8 bytes is all it is. I still can't get over that even after all these years. It's just the tiniest little thing, and then all of your data. You've got a pad to make it a multiple of 16 bits, to make it a multiple of 2 bytes. So for a very small header, here's how you calculate it. You split things up into 2. You create the sum. You flip it, and that's what goes in for your checksum. And the idea is when you add it back, do you guys remember how checksums work? Completely or sort of? Sort of? All right, so the idea with the checksum is you add up all these numbers, you ignore the overflow on some numbering systems, on some of them you add it back in again when you're done. But this one came up with a sum, and all they did was flip the bits. That's exactly what they did. So this number is the sum before the checksum, right? This is only the checksum. If you add these two together, the sum and the checksum, what do you get? All ones. So if I take this packet, which the sum of which is just this number here, and I also insert now into the checksum field, where it was all zeros a minute ago, if I insert this value now, when it arrives at the other end, and all I do is add all the numbers together, what should I get? It's the same thing that you just said. All I'm doing is adding up all the strings that previously were the sum, but I'm also adding the checksum to it, because I've included it now in the packet. So if I get all ones out, I'm good. If I get anything else, the packet's been corrupted, and I can throw it out. It's not a very strong error detection, but it gets little errors. Right? So it doesn't need to be perfect. We don't have a whole lot of time when sending UDP. Okay. Oh, by the way, there's some special trick values for checksums. With UDP, if you send all zeros in the checksum field, it basically means the checksum was not calculated. And you can decide to omit doing that. It's optional. You don't have to calculate the checksum. So if it's in there with all zeros, then we're okay. When we go back and look at our packets over here, these were definitely not zeros. So that's not a good explanation for what's going on here. In fact, they're all changing, but they're all wrong. Because when I told it to turn them on, you remember all the screen went black for the most part. Those are corrupted checksums. So it's worth a little bit more digging in the Wireshark blog or the Wireshark user community. All right, let's see. How do you know when you add things together that the checksum really doesn't end up as all zeros? I mean, if I'm going to use all zeros to represent a special message, basically that I chose not to do a checksum, then that must imply that there's no other circumstance when those zeros would have otherwise been generated. Can you ever have a zero? Why not? Yeah, so all zeros means you have nothing in the fields, essentially, and that's not a valid UDP. You can't have a port number of 0. You can't have a length of 0. So you are going to have something other than zeros in there. And they go to great lengths to make sure that happens. So when the sender complements the sums, the second complement is needed to avoid confusion. It never happens, blah, blah, blah. You can read more if you want to see it. You guys know exactly how encapsulation happens. We don't need to spend really any time on this. You start with the message. It gets plugged into a UDP packet, then an IP packet, then a frame header, and it gets sent. All right. So what about queues in UDP? With UDP, there's a basic incoming and outgoing queue. So we show the daytime client and server. It's the one that was running on port 13 over on the server side, and port 52000 on the opposite end. So you send something out, the outgoing queue, to port 13. It arrives. It says it's coming from port 52000. So the port is built for who's sending it to you. The port's built for the arriver. And you queue these things up. All of the packets from all the users around the world, they all show up in the same queue. UDP does not separate the queues because every packet is one and only one. There's no such thing as a stream of packets or packets that are connected together or packets that represent a conversation or handshaking or connections. None of that stuff exists in UDP. You can implement that in your app if you want, but at UDP, this packet could be from you, this one from me, this one from you again, this one from someone else. It makes no difference. And so when I send stuff outgoing queue, I don't worry about mixing it in any particular order. I don't number them. I don't try to figure out windowing if they got there or not. I don't care about any of that stuff. It's super lightweight. So if you've got lots of processes that are trying to send things out via UDP, then UDP just has some round-robin scheme for making sure everybody gets a chance to send something. It's a multiplexer. This is the same issue in a router with weighted fair queuing and non-starvation queues, etc. So it's connectionless, and a typical application will be things like DNS. DNS seems really important. Why would we use it? Because it's super lightweight, and if you don't get an answer, you're going to try again. The application will do that. One may wonder, then why don't I do web pages that way? Because I'm impatient with those as well. Those are streams. You can't get a whole stream of stuff into one packet. With DNS, you can. You can get an answer back in one packet. Client-server email can't use that because it sends an email message that's longer than a packet. So you need to make sure they all can be sent together. So there's the argument for you right there. And then very large text file as well. Some applications will switch between UDP and TCP. And for this, the very surprising fact is when you have a port number reserved by the Internet Assigned Numbers Authority, and you have to apply whether it's going to be for TCP or UDP, they reserve the other one too. So one would say, well, you're wasting half the ports. But port 80 is reserved on both sides, UDP and TCP, and eventually they made use of it. DNS makes use of it. It will use both sides. So you can switch back and forth. The port number, they're different. They're going to go to different programs, but they just reserve both of them in case you need them. There's a more detailed description of that in the TCP IP guide that I showed you a URL for a few weeks ago. Okay, so here's a really simple version of the TCP module. It has an input module where packets are coming in from the network down below. This is the IP layer. You have your application layer up at the top with a variety of processes, and data is arriving. It gets demultiplexed, put into a queue per app. This is the very last step, so it is a queue per app, and it pops it up to the program. But the packets can be coming from anywhere. They can be coming from a whole variety of computers, all mixed and matched together. But there's a queue per app. And when you are sending things out, there's basically no queue. You get in line and you hand it to the output module and it leaves instantly. There should never be a line. Nobody's waiting to retransmit or to see how it goes or any of that stuff. So we can look at a little bit of code. The block basically says, look for a free entry in my table of queues. So I have a certain amount of memory allocated here for queues. When it's full, I can't take any more connections. So that doesn't happen very often because it's usually an undesirable feature of an operating system. So here's your control block module. You look for a free entry. If it's not found, throw one out. Otherwise, whether you had to do that or not, create an entry and stick the process ID and the port number in there. That's what we know so far. Okay, and when a datagram shows up, if there's an entry in there, check to see if a queue is allocated. So I built a control block. I've actually said, okay, I've heard of this port number, I've heard of this process, but so far, no one's come to me to give me data to queue. And now you have data. So you're going to actually allocate a queue only when someone proves to you they have data for that app. We will not create a queue for you until data starts arriving. Some things will never have data that arrives. All right? If you can't find an entry in the control block, it doesn't exist, then you send an ICMP error message back. Port unreachable. If there's nobody that's bothered to open up a connection for that port and say, I'm listening on this port, then there's nothing for UDP to do. It can't pass the hatter and say, does anybody want to listen to this port? Programs have to do it. All right? And you throw the datagram out, basically. The output module, it's super simple. There's no queues. There's none of that buffering. It's what's on the right-hand side over here. You get a packet, you send it. Repeat. That's all you do. So here's a control block table. And when you first when a program first wakes up and it opens up a socket, let's say, for UDP, what the operating system will do and the UDP code will do is mark down the process ID and the port number. And that's it for now. It'll mark down the process ID and the port number and state that this table entry is in use. it will not write down a queue number until data has arrived. So if I look at this diagram, I can see that there are 3 UDP processes running. 2 of them have received data. I can tell that by looking at this chart. They have interesting consecutive port numbers. I'm not really super comfortable with that, but you can assign port numbers however you want. There's no requirement that they be consecutive or not. So let's see what happens if we start changing this. So let's say a new datagram arrives for 520112. That's down here. Does a queue find it? Yes, a queue has already been assigned to the port. We don't need to do anything with the queue. Nothing changes. So far, so good. The next thing that happens is a process starts up on my computer. He is assigned port number 52014 by the OS. So he wants to register a socket for UDP. So he sends his process ID and his new port number to the control block. It will find a free entry. And if I go back, you'll see I had 2 free entries in here before. It's going to take the first one right here, and it's going to write down his process and his port number, and that's it. The next thing to happen is a datagram arrives. What in the world? Datagram arrives for port 52011. That's here. Let's go back one. It did not have a queue assigned to it, so it will assign a queue, and that's it. It'll just assign a queue, and now there's some memory allocated. And now one arrives for 52222. Not in my table, so I drop it and send an ICMP error. I chop off its head, include a little neck, put it in a box, and send it back. I told you you guys would remember that. And you do, right? That's what you were thinking of before I said it, right? Yeah, and you'll remember it. As long as you can remember it, then I'm good. All right, so believe it or not, we just did UDP. That's it. Oh, man. Are you in for something now? TCP is like a billion times worse. So I will close out. We will not finish TCP today. I'll get us into it a little bit. We need some, quality alone time with TCP to really learn about it. Yes, sir. We sent it because we looked for the port number that the user was trying to reach. They sent us a message and asked us to deliver it to this port number. And we don't have any process running on our computer at the application layer that has registered that it's interested in seeing data that arrives for that port. And so the UDP layer will tell ICMP, kick this thing out and send an error message back. So the problem with this is that one way to hack a computer is to try sending a message to every port number and see where you get error messages back. It's called port scanning, and it's a known vector of attack. You're trying to figure out what ports are active, and you know what programs run on lots of those ports, and you know what bugs have been published for the software that runs on those ports. And so once you have a list of the programs that are running, you try all the bugs. You try things like send the daytime server a message that's got a time that cannot be decoded. It's an incorrect format. And see if you can get some crazy message back that suggests that it's crashed, but it still left the socket open. And so now you can send, right? So it's very hard to figure out what to do with something like that, but there have been lots of people that have figured it out. So lots of systems will shut down port scanning. They won't even let it happen. So I'll bet you if I tried pinging a site with incremental port numbers, I wouldn't get anywhere with it. I wouldn't get ICMP messages back either for lots of sites, because that's kind of an old-fashioned way to hack. All right? Okay, so with TCP, we're just going to get far enough into this to kind of show you guys. I think I can get far enough. I may not get completely. We'll see if we can get to the header. That's kind of what I'm after, see if we can get to the header. So This has lots of state transition diagrams that you remember from last year if you took 2018. So we'll talk about flow control and congestion management. They're completely separate topics. I will say TCP is far more interesting as well, and it's been sort of rebooted in the last 6 months. There's a different variation of it that's now being distributed that I think will dominate us within a couple of years, or some variation will. So lots of stuff to go over on this. It sits in the same area as UDP. That's no big surprise. We already know that. Here is a list of well-known ports. Pretend you care for a second. Okay, done? Let it pass? All right, we move on. And this one builds basically a stream. It gives the illusion to the application that there's a constant connection between two sites, and anything they pour in one will pop out the other, like a tunnel, or like a hose, like a pipe. So that's the illusion it has to provide, is something to support a stream of bytes. Wait a minute, what do you mean stream of bytes? Aren't these things in packets? Yes, but what's delivered to TCP are streams of bytes. They're delivered in messages, but the size of the message and the number of bytes in the message has no resemblance whatsoever to how many are put into a segment by TCP. And so it's much more accurate to think of messages arriving on the top floor, and everybody gets off the bus, and they go down the little spiral staircase, one at a time in a row, and they get on a little rowboat, however many can fit, and it takes off. So the person up above has no idea what's happening down below, and vice versa, and all they see is just an endless stream of people coming down the stairwell. And depending on what's going on, they can use big boats or little boats. But it does provide this concept of a stream of bytes. We have to use some data structure to get it there. But you could write, absolutely could write a version of TCP that didn't use matrix-sized data structures, that really use some sort of a endless linked list stream of data, because that's what it's really trying to provide, is an endless stream. So you would think, well, that sounds like streaming. I mean, it even has the word stream in it, but it's terrible at streaming. Sometimes you will see TCP being used for streaming, but only when the site prohibits UDP packets. If you're forced to use TCP, everyone will use it. YouTube can use TCP. And you can just use Wireshark to figure out what YouTube's using. Is it sending you stuff via UDP or TCP? And some sites will prohibit it. Okay, so here's this example of a buffer. This is one way of showing it. So it's a circular buffer, and it's something like looking down from the top at a spiral staircase. So you have things that are empty. These people are just got off of the staircase. These people are waiting to get on the next boat, and you have room. These steps are empty, and you have available for space. So then when it's time for the next byte to be sent, you send it across, and at the receive side, these users get off the boat. They start climbing up the staircase to the top. When the staircase is full, you can't take any more boats. How does the staircase get emptied? When someone comes to say, next 5 people walk on in. So this is like waiting in line at every government office you have ever been to in your life. Right? Next 5, next 3, they start counting you off, right? So that's what's going on. You have to wait for someone to come get you. People cannot leave the stairwell on their own. So packets cannot leave buffers at the receive site. This is why the receive buffer size is constantly being sent back. I got room for 8 more people. I got room for 4 more people. Stop sending me more people, whatever the message might be. All right, we saw that in lab. Okay, so moving on a little bit. What TCP will do is take as many of these people off the stairwell at a time and put them in a datagram, a boat, and send it across to the other side. So we'll have to stop using the boat datagram. You're probably really happy to hear that. But we'll have to stop using it now, because where it falls apart is when you start cloning people and resending people, and that's like, you know, I'm sort of in quasi-religious territory there. offend some people, perhaps. All right, so that's what's going on. So it provides the services we talked about. It provides numbering. It has flow control and congestion control. Those are the two big ones. It does provide some mechanism to recover from errors. So the bytes are what are numbered. Last year, when you learned about TCP the first time, you were taught the packets are what are numbered. I can send 10 packets. I can send 20 packets. That's not how it works. You're keeping track of byte numbers. The sequence number is byte numbers. That part is the same. We did learn that. But there's nothing that says my window is 20 packets big. That doesn't exist. What really happens with TCP is you say, I've got a window that will let me send 1,200 bytes. And independent of that, TCP has been negotiating a packet size with the other side based on defaults and experience, how the connection's been going. So it may reach a agreed upon packet size of 100 bytes. So it divides 100 bytes into 1,200 bytes in the window, and it says, okay, that means I can send 12 packets. And you get an acknowledgement back. The acknowledgement may cause the number to go up to 1,205. You still send just 12 packets. 1,210, you're still going to just send 12. Until it reaches 1,300, you won't send another packet. Doesn't matter what the window size is. If it's not an even multiple of a packet, you will only send full packets. You will not send partially filled packets unless there's a flush or a timeout or something like that happens. So we start with a randomly, not really random, an arbitrarily generated number. And so if segment 1 starts with sequence number 10,001 and it's 1,000 bytes each, then it goes from 10,001 up to 11,000. The next one starts at 11,001 up to 12,000. So what you're going to send is the first byte number in these packets. That's your sequence number. So for this one, it sends packets 13,001 to 14,000. Therefore, the sequence number that is included in the TCP header says what follows begins with 13,001. And you say it's 1,000 bytes long. So that part's, yeah. Yes?
Segment is a bunch of packets with same sequence number, or each packet has its own sequence number?
Every byte has its own sequence number, and it's like every person on the stairwell has their own number. So whichever, when the new boat pulls up, and you're ready to start putting people on the boat, you ask the first person getting on the boat, what number are you? And they say, I'm 643. And so you write down 643 on the front of the boat. That becomes your sequence number. Right? And how many? So you know, and they're all numbered sequentially. We're very, very careful about that. Everybody stays in line. So I don't tell you the last number. I tell you the first number and how many there are. You can figure out what the last number is. So why do I do that? Why do I not tell you the last number? Why do I just tell you the first number and how many bytes are in this datagram? Exactly. Maybe the last one won't get in. Why? What would cause the last one to not get there? It's in a single packet. What would cause some of them to get there but not the rest? It starts with the letter F. Fragmentation. It makes it really easy to calculate fragmentation. If you say, here's a fragment, they get off this one boat, and they get on another one. You know the first number, you know how many are there, you send it on. The next guy, you ask him his number, he gets on the boat, how many are there, you send it on. And on and on and on. That can be done really quickly with the first byte that's there, not the last one. Right? So there's some elegance to this. And the boat analogy, does pretty well work in this case still, right? Except people are numbered and they're always in line. But the stairwell is a pretty good way of kind of breaking down this packet thing. You think of a stairwell, people get off one at a time. We kind of have a good intuition for that. So if you think about the spiral staircase, then like we have here, they're not exactly spiral, but they do this, then it's a good model for us. Did that answer your question? Okay. So the value is the number of the first data byte assigned to that segment. The acknowledgement field tells you the next byte of the person you're expecting to receive. It's basically saying, I have an empty spot for number 72. Send me 72. So you're always looking for the next one. So the acknowledgement numbers are cumulative. So what TCP will do, and we see this in labs, and some of you I got to talk to about this in some of our labs because it wasn't the point of our lab, but we noticed it. You don't get acknowledgements back for every packet you send. The TCP receiver knows exactly how long you are going to wait before you get nervous and resend a packet. It knows. It also knows how long it's been taking to get packets round trip back and forth. So it can calculate when it can send the last acknowledgement at the last possible moment that will reach you before you freak out, before you say, it's lost, he's lost at sea, we need to send another boat. Right? So it knows when to do it, and it will intentionally wait and suppress sending acknowledgements. Hey, don't you think you should tell him I made it here? Just hold on, wait a minute. 50 more people. Hey, don't you think you should tell him I made it? Wait, just wait. Okay, now we can tell them. So you send a bottle back across the water and it makes it there. So that reduces the number of packets that are sent on the network, and the golden rule is send as few packets as possible, as short a distance as possible. If you design your protocol with that, you're doing a good job. Okay, so that's what the acknowledgement does. What happened here? Too big. Okay. Let's look at the packets, and this is where we will end today. So this is our last section. So you've got a format of 20 to 60 bytes at the beginning for IP, and then you've got, actually I think TCP has options. It can also be up to 60 bytes. I think that's right. I've got my head still wrapped around IP, so I'll have to look at this a little bit with you guys again. But TCP's got variable length. You can have lots of options. And you've got source and destination port number, sequence number, and acknowledgement. These are sequence numbers. So what do you think happens? Let's say my 32-bit number that I pick is, oh, they're playing music already out there. Is it something I should let you guys go listen to, or can you tell what it is? It's hard to tell, isn't it? All right. If it's Natalia Lafourcade, I'm leaving. I'm letting you know now. Oh, absolutely. I know all of her songs. I've seen her live many times, and she comes to Houston like twice a year. Oh yeah, it's packed. And the whole audience like sings along, you know, Nunca suficiente para. It's like really funny. And she sings songs from her new album before she came out with the new one. So yeah, Houston loves her. She's all only. Well, she talks to the crowd some in English as well. She can speak English okay. Not as good as you can, but it's okay. Better than Peña Nieto. I know. Don't stop. I have Trump to deal with, so just don't even go there. You have it way better than I do. Oh yeah? Well, good. He shouldn't. I don't think. That'll just take some wind out of Trump's sails if he has to watch somebody translate it, I guess. So, okay, so let's suppose this is my sequence number that I generate. What's going to happen pretty soon is I'm going to get to this, right? And what should my next byte be numbered after this? It's only 32 bits, so pretend that's 32 bits wide. What happens when I reach this number in my sequence numbers? It's not usually going to be at the beginning of a packet. That would be like crazy coincidence. It'll be some byte buried in the middle of some packet that will have this sequence number. And the very next byte should be numbered what? Secret. You just cycle over, just like an odometer in a car. All right, so what's the implication from having a number block that you're going over and over and over and over and repeating? And you're using this to make sure packets are arriving in exactly the right order. You will loop, but there's a... Yeah, in fact, the implication is you will never have a window so big that it has enough sequence numbers to have the same number twice. Every window you'll ever send, the total accumulation of sequence numbers will start at one point and end at some other. It may start here and end here, or start here and then it may start at a high number and end at a low, or vice versa, but it's never going to loop itself. If it does, you're asking for a nightmare. First of all, you're asking for an attack, because it'll be an attack vector. So that's why it's so darn many bits. Now the problem is that lots of providers now hack TCP, and Netflix does it through Akamai. When you see a local Netflix server in Monterey that's part of your ISP, and you ask for a movie and it says, oh crap, I don't have this movie, it'll go back out and get the whole 60 gig file. And actually, it's probably going to get 5 or 6 or 10 versions of it, so it's probably hundreds of gigs, because it may not know exactly what size your screen is yet, and maybe it does. So you got to design that. You got to figure it out. But it's got, no matter whether it's 10 or 100, it's got a big problem on its hands, which is how to send that massive amount of data quickly enough that it doesn't seem like it's any different to you than if it had been sitting here on the hard drive the whole time. So you've got maybe a second or 2 or 3 to get it across. There's lots of ways of doing it, but one way not to do it is like this. To send acknowledgments back and send a window's worth of things at a time, where maybe you send, I don't know, maybe you send 10,000 bytes. Maybe each of these is 100,000 bytes. It's still going to take you lots of round trips. All of your time is eaten up here in the round trip. So you want to eliminate the round trips as much as possible. So what you'll do is hack TCP. So instead of sending this, you'll send one request and you'll get all of it back in one packet. And the guy will be like, thank you, you know. So you get it all back at once. And you can do this if you're really confident that the network is not congested, it doesn't have jitter, you're not going to lose track, buffers are big enough, it's not going to overflow anyone. So you had better own the whole network between these two, and that's exactly what they do.
That's like 2G packets?
They're huge packets. I don't know how big they've made them now.
That's
They're way out of spec. They're completely out of TCP spec. They're off the RFC reservation. It's a custom version of TCP. And they have a lot of success doing this, so everybody's doing this now. But you have to run it over your own network. This would be like deciding you're going to send a vehicle from here to Saltillo, but the vehicle is 500 feet long. Can you do it? You can if no one else is, you know, if it's articulated, right, like a train. Exactly, like a train. That's how trains work. You can do it if it's a train. But then that implies things, right? You're not stopping at stoplights, and you're not having to deal with pedestrians. There's no competition for the route. There's no drop things. There'll be no accidents. That will not be allowed to happen. And you probably have 2 redundant fiber routes that are both sending it at the same time. So if one of them craps out, you can get it from the other one. So for example, all broadcasts for the television networks, they receive 2 copies of it, they process 2 copies of it, and they send 2 copies ready to go. If anything happens with one of the transmissions, like on a program, the engineer goes bonk, and it flips over, and it continues sending from the other one. They don't ever, everything's redundant. So you'll do that on a network like this as well. All right, so, yes?
Why does Netflix use TCP instead of using TCP?
Well, why not? I mean, if they can hack it to get it to do what they want, and they can get all of the error checking that they need, and they can still number and make sure things that they may still use it to send regular TCP stuff that's not, not this big, perhaps, then it's still useful. And also with TCP, there's this concept of a window at a time, and you do get acknowledgement that it arrived. So they would still like to know, they would like to see an acknowledgement. UDP will never send you one. It will never tell you whether it made it there or not. It couldn't care less, right? So there are still some things that you'd like to do. But there's probably 100, 200 versions of TCP now. I mean, so many PhD research projects have been done on it. People just like, feel like modifying a new version. The nice thing about it is you don't need permission. You could write a new version of TCP this evening and use it over the internet. No one will stop you. As long as you're communicating with someone at the other end that writes that you've given code that will do the other side of it. There's no restriction. IP couldn't care less. So the TCP segments you got, IP will break them up into pieces if it needs to and put them back together at the other end. You'll still get your same TCP thing back. Even if it's fragmented by IP, you can still get it all back in one piece if you need. Yeah. Okay. So back to the sequence number thing. One reason I claim that you have the sequence number and the link but not the final one is in case it got fragmented. Fragmented is usually invisible to TCP. Things will get put back together before IP will hand it back up. But what TCP and IP will do, if it's well designed, is they will negotiate with each other on how big of a TCP segment should I be sending you in the first place. Because IP will complain, stop sending me these giant elephants that I have to slice up into bologna to put them out on the market. Stop sending me things that big. I can only handle 1,000 bytes at a time. Don't send me anything bigger than that. In a well-designed block of code, you'll negotiate that, and you'll adjust as time goes on. So that's one reason why you may have to adjust these things as they happen. Okay, so we've got the header here. There's a whole bunch of other flags. Great, more flags to remember. At least we've got 16 bits where we need them. We're not having to do multiples of 4 or multiples of 8 or anything like that. Window size, urgent pointers, all those things are the bits we want. Here's where we run into trouble with header length. There's only 4 bits for the header length, and so it can be between 20 and 60 bytes. We already know what to do. 60 bytes would need 6 bits, so I want 6 bits, but I got 4. Therefore, I'm going to force you into multiples of 4. So your header length can be 20, 24, 28, 32, 36, etc. And that's it. So I take whatever number's in here and I multiply it by 4, and that's my header length. You may not have a number that's smaller than 4, or 5 rather, and you may not have one that's bigger than 15. Well, you can't in 4 bits anyway. 15 is as big as you can get. Exactly like IP. Remember?
Yeah.
So the value for header length, headers can be 20 to 60 bytes, right? So how do you encode 20 to 60 in binary? Well, 20 you can do with 16 and 20, right? That's not right. 2, 4, 8, 16, 8, 20, one more 0, right? And then 60 is what? Well, 60 you need another one almost, right? So you need 32, and that leaves you with, you need 32, 40. 8 will give you the 40. Then you need 20 more, which is back to the 16 and the 4 again. So something like that. That's not quite right, but you understand. We don't have this many bits. We are given 4 bits. So we're going to pick the high order 4 bits. We're going to force these to be 0. Since you can't know what they are, you're not allowed to send them anymore. And so the only values you can have in this kind of scheme is 0, 0, 0, 0, 0, 0 hidden, 0, 0, 0, 1, 0, 0 is hidden, and so on. All the way to 1, 1, 1, 1, 0, 0. So what's this number? This is 0. What is this number with 0, 0 in the end? That's 20. What's this number? 60. So valid ranges between here and here. We will tack on zeros at the end, which is the same thing as multiplying by 4, and that's how you will tell me how big your header is. You will only give me the upper 4 bits of a 6-bit number, and I will add the 2 zeros myself, which is the same thing as multiplying by 4.
Why the size of data rise?
Why the size of data?
Okay.
Because you can have any size TCP datagram you want. You'll probably stick to that size once you pick it, but first you have to pick it. TCP will give you a default. You'll try that one first. 1500 bytes is really popular, for example, and you'll have a 36 byte header, so you'll have a 1536 byte UDP. The size of the header depends on options that you need with TCP, and so you can supply other things in there. We'll look at some of the options, but it's basically left as a blank chalkboard for protocol developers to pack other stuff. It is not part of your data. It's purely part of TCP. So let me see if they show us any options in this slideshow. Why is it not doing fun? Okay, 40 bytes of option. Let's see. There's 1 byte and multiple bytes. So there's SAC options. So end of option list, no operation. Multiple bytes is maximum segment size. Timestamps, we'll see some of that. Window scale factor, whether you have certain types of acts, a certain type of act thing acknowledged. So it's things that vary the protocol, like you're thinking. Right? So there's room in there to do stuff. No op would be one that says, I don't want you to do anything with TCP, I'm just trying to send something. Okay, so we're going to fall off the deep end here next time really fast, because we're going to get into this stuff, but I can't do it in the, we can't do it at the end of a 3-hour span. That's just, I might as well sing a song or something. You'd have as much chance of remembering that next time. But do you guys remember these types of diagrams? Do you remember seeing these where you have slow start and additive increase and then multiplicative decrease? Okay. So did you take the class from me? Okay, good. Because that's in the syllabus. It's supposed to be covered. It was for my students, but like every university I've ever heard of, no one checks to make sure the professors are all teaching all the stuff exactly the same way. It's like old world artisan skills. It's like an apprenticeship. You're stuck with whatever I want to say. It's like, you got to be kidding. And in some places, online courses are much more rigorous about making sure, no, you've got to teach these things. So it's a big problem when you get to medical school, because in medical school, if you don't want to be in court all the time, you better learn exactly the right stuff. In fact, the way the medical field works is really interesting, and I was in the faculty of a medical school in Houston for a while not as a doctor of medicine, but as IT, and they have these disease states, and they have protocols that are intended to specify the steps that you need to go through to get someone from a disease state back to a normal state. So every disease has a name, has a number, and it's assigned to a professional organization of physicians who specialize in that disease. And they're called colleges. So, for example, how to perform C-sections on a woman giving birth is managed by the American College of Obstetrics and Gynecology, ACOG. They publish the accepted set of standards. So if you don't want to get sued, just follow that recipe. Exactly. If you vary from it, you're asking for trouble. So the way these IT systems get built that we develop for these doctors is they don't give them any choice. They say, like, have you administered this drug? Have you taken this reading? Have you counseled the patient on this? Have you done this lab test? And blah, 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 blah. And record these values, and it'll, kind of walk them through. They have to stay pretty close to it, or they can open themselves up. So all a lawyer has to do is show up and find, like, well, at step 13.b, you did not follow the right step, and I have a doctor that says that's what caused the problem. So it's very rigorous, very different than undergraduate education. So I've always wondered, like, how do first-year medical students make the adjustment? It's unbelievable. But the writing IT stuff for it's really fun. It's really interesting. You can get a lot of stuff done. Okay, guys, have a great week. One of our last 4, or did we decide 3? 3. This one, 3 more after this, right? Okay. And then it'll be goodbye. Of course, if immigration's unhappy with me, this may be goodbye. You never really know. We'll see. Let's hope not. Yeah, we'll see. All right.